Hello again. Now we will continue with the hands-on session on modeling of large-scale social data. So for the hands-on session, since it is an interactive session, you can raise your hand and we will unmute you so that you can ask your question. But if you prefer, you can also type your question in the Q&A section. Yes, Maria, if you are ready, we can start.
Yeah, thank you very much. Okay, so this hands-on session, as you saw, a lot of analysis kind of is focused on network analysis, okay? And when I started almost 20 years ago, at that time we did not have any kind of tools to actually analyze any kind of network. We used C and we wrote our own code. And then there was a development of different kind of tools. And somehow Python entered this field. You also have a similar tools in R if you're using R. But I prefer to use Python because it kind of got quite developed in the past 20 years. And there is a whole session of physicists who are actually studying or developing tools for network science. And there is a tool called NetworkX, which you can install in Python. And usually I use this tool to study my networks. However, this is a CPU-based tool. And as you will see in the next few steps, it sometimes, especially when you work with the large networks, it's quite slow. And nice thing happened in the past few years where our colleagues actually developed a network kit tool, which you were set to install. Network kit is actually a tool used for large-scale network analysis, and it actually uses it's written in C, but you also have a Python module for this, and uses OpenMP for shared memory to actually parallelize this process. And it's basically developed to use it on GPU resources. So it's kind of making the whole analysis of networks much faster. It's more efficient and very, very interesting tool to use if you want to use it for large scale data. First, I wanted to show you how we can actually compare these two tools. They actually have a very similar syntax. So if you are very much familiar with NetworkX, which most of the people who actually study networks are, it's not that complicated to translate to NetworkKit. The it's not a problem, it's still, it's a relatively younger module that is developed. Unlike NetworkX that has very broad scope. So it has a lot of algorithms that are already developed in NetworkX. It's in development for, I think, at least past 15 years, something like that. So it's quite refined, has very few bugs. Unlike that, NetworkKit kind of has it's a little bit buggy. So it's still in development, and they actually offer in their documentation a possibility to add your own code as a part of NetworkKit solution. So what we will use in this, we will use, of course, NetworkX, because I want to show you how faster NetworkKit is compared to NetworkX. I will use, of course, NetworkKit, Matplotlib for plotting, NumPy and SciPy are always needed in this kind of analysis. And actually, pandas as a module that allows us to easily manipulate with large data sets. So we are going to import this. I also wanted to import AutoTune, because this way we can actually look at how much time each cell takes to run. And I will show you a little bit how this, to compare NetworkX and NetworkKit on very kind of interesting graph. These are hyperbolic graphs. There are many generators of graphs in both NetworkX and NetworkKit. I used here NetworkKit generator for hyperbolic graphs. It's a graph that has, in this case, 5 million nodes. And it's quite large graph, because we usually deal with much smaller graphs because of the velocity, or because of the time of running. We want to deal with smaller graphs that can easily analyze, that we can easily analyze. But with NetworkKit, these limits are kind of much broader. So we are going to generate this graph. And just to show you, how many nodes and edges this graph, how many nodes and edges this graph has. So it's kind of not very dense graph. You will see later that we can actually use an overview and get all the information about these graphs. But before that, we also want to, because we cannot use the same container for graphs in the case of NetworkKit and NetworkX. So I want to translate my graph created in NetworkKit environment to NetworkX environment. And for this, I will use a tool or a function that already exists, or a class that already exists in NetworkKit. It will take a little bit of time to do this, but before that, let me just say one thing. So NetworkX and NetworkKit both have these structures or objects in which they store graphs. In both of the cases, you can either first start by defining this object and then adding nodes and edges, or you can actually use these graph generators to create it right away. So as you can see, we translated our graph that was created in NetworkKit to NetworkX. And now I want to show you how you can do a very simple kind of analysis, and how is the difference in time in the case of NetworkX and NetworkKit. First, we will use NetworkX to find the number of communities. What are the components? What are the components? So whenever we create a graph, that graph doesn't have to be fully connected. This means that there doesn't have to be a link or a path between every two nodes in the graph. So usually we have networks that are disconnected. So this means that they have groups of nodes that are connected with each other, but are not connected with the rest of the networks. And these groups of nodes are called components. Here you will see how we can easily use already existing functions to look at whether our network actually is connected or is not connected, and to actually find all of these components using either NetworkX or NetworkKit. So here the function was done by NetworkX. We can use the same approach now to actually calculate these components in the case of network kit. There is a slightly difference with network kit. Unlike network X, where you only have one line of a function, here you will need to first assign a class for or what you want to do and actually run this. You can also do this in one line by just typing run here, but I want it to be more precise. So the number of connected components that was found by network X is 205,500. And as you will see, the network kit will find it with the same number of components. What is more prominent is that it's actually 10 times faster than network X. So already we see that using GPU resources, we can actually be much faster than network X. Why is this important for us? Well, okay, for the network of this size, obviously this is not a big difference, but sometimes you will have much larger networks. That's one thing. And the other thing is, as you will see later, we will do other types of analysis that actually demand much larger time. For instance, I mentioned this core periphery structure. It takes us with network X few days to calculate this core periphery structure for one data set in our case. So we are actually thinking about trying to use network kit for these kind of calculations in the future. Now, usually we want to find out which is the largest connected component in the network. And with network X, this is a kind of simple. So you find all connected components of the specific network. So this is this line. And then you sort this. This is a set, or it's a lists of nodes. And then you basically sort this list according to their length. And you will find the largest component using this approach. The same approach can be used for network kit. So we already calculated components, connected components of the network. And now we only have to actually get their sizes and sort this dictionary and then print the size of the largest connected component. Sorry. We also need to, this is the smallest, sorry. I have. Okay. Sorry. I think they made a mistake here. I apologize. Okay. And we will use reverse here. So we actually have the first component as the largest size. What we can do further is we can actually calculate the clustering coefficient using network kit. It takes like 20 milliseconds, but as you will see for network X, it will take much longer time. This is a component that actually takes, so this is an algorithm that actually has to go through each node, and then through each first neighbors of that node, and then first neighbors of that node, so second neighbors of that specific node, to actually check whether there is a triangle forming between three nodes in the network. So it's in like the most, so to say, rudimentary sense, is an algorithm that is n of the order n over 3. So the n is the size of the network. As you will see, the network kit actually calculated this much faster, and network X will take some time to do this because it's a slower algorithm and it doesn't use a GPU resources for this. As you notice, there is a difference between these two networks, these two values, and this is the reason usually how you calculate. This is the average clustering coefficient. So this means you calculate the clustering coefficient of each node, and then you calculated the average by averaging over all nodes in the network. And now it depends whether you are including nodes with zero clustering or not. Network kit, I would say it doesn't include nodes with zero clustering. So it averages only over nodes that actually have non-zero clustering coefficient. And network X is actually averaging over all nodes in the network. So that's why you have a slightly lower value of clustering coefficient. So if you're using each one of these algorithms, you have to be a little bit careful with this. The next thing is network diameter. And here I'm stopping comparing with network X. The next thing is a network diameter. Why do we need network diameter? Sometimes we want to understand how far or what are the most distant nodes in the network. Network diameter tells us a lot about how network evolved and how this network is kind of put together in that sense. Many of the social networks, technological networks, and biological networks are usually networks of relatively small diameter. So this means that you can have really large network with diameters that are quite kind of low. And for these reasons, we want to actually see whether our networks is a small world network, so-called, or not. So here is a very simple way of finding the largest connected component in this system and making actually a graph out of this. So basically what you do is you find the largest connected component, find the nodes of that component, and they make a subgraph of it. And then you use this subgraph to actually do the analysis. Why we do this? If we want to calculate the network diameter in the network that is not connected, so it consists of several disconnected components, we will get an error. Why? Because there is no diameter between two nodes that are not in the same component. So you will get an error for calculating this. So what you will do in this case, if you really want to find out the diameter of each of your components, you will create a subgraph for each component and then calculate the diameter of this specific component. In this case, we would say that our network actually has diameter that is infinite in that sense, okay? So what we will do, we will calculate the subgraph of the largest connected component in the case, and we are using network kit, and we will run diameter. So diameter is a distance function. You use diameter on this new graph. You can do it also in one line, and then you will get the diameter of 60. The size of this largest connected component is 2,276,077 nodes, and the diameter is only 60. So this is, while it's relatively large number, this is still a network of relatively small size. Hyperbolic networks are actually networks that are kind of embedded in space. And as a consequence of this, their diameter is slightly larger than in the case of real-world networks. What we can also look at is assortativity index. So network X can calculate this. Why I didn't use the diameter also to find in network X is that it really takes a lot of time. And I didn't want to lose this time for this, but believe me, it's much, much longer because this algorithm is relatively slow compared to other algorithms on networks. And due to this, we can see that network kit is already kind of more advanced in this sense. So what we can also calculate is an assortativity index. So assortativity index shows us how nodes of different degrees are connected with each other. What is the degree of node? Degree of node is the number of connections that that node has with the rest of the network. So it basically shows how many first neighbors a node has. In social networks, nodes of similar degree tend to be connected with each other. So usually we say that popular people tend to be connected with popular people. Less popular people have tendency to be connected with less popular people. Unlike, for instance, biological network, where this is the opposite. In biological networks, nodes of high degree tend to be connected with the nodes of low degree. In the case of social networks, we say that these networks are assortative. And in the case of biological networks, we say that these networks are disassortative. So basically, we look at the correlations between degrees of the node and average degree of their neighbors. And I will show you later how we can calculate this. As you can see, again, network kit is much faster than network X. Yeah. Someone raised the hand.
Yeah.
Would you like to ask?
Yes. Now I think.
Yeah, I had a question.
Yeah.
I was just curious. So, you said for social networks, this degree of assortivity coefficient.
Yeah.
I'm sorry, the terminology. I'm new to the terminology. With lower, the nodes with lower coefficients or something like that are more connected in biological networks, and with in social networks, or it's the opposite.
I can repeat, okay? So in a network, you can, for each node, you can calculate number of first neighbors that that node has, okay? So this is a degree of a node, okay? So each node has a degree of certain number, okay? You understand that?
Yeah, I understand.
Okay. And now this is a property of a node, so to say, okay? And then you can look at the correlation of how nodes of different degrees are connected with each other, okay? And in the case of social networks, nodes of similar degree tend to be connected with each other. So basically, if you have a node and you have first neighbors of those nodes, and you calculate their average degree, the function of this average degree will grow with degree of the node. You will see later the exact how this looks like, okay? On the other hand, in the case of biological networks, this function of average first neighbor degree decreases with no degree, okay? So this means that basically in the biological networks, nodes of large degree, so the nodes that are connected with large number of nodes, tend to connect with the nodes of lower degree. So this means that they're connected with nodes that have only few first neighbors, okay? On the other hand, in the social network, it's the opposite. People who are very popular, so have very high number of friends, tend to connect with people who already have high number of friends. So we say for these networks that they are assortative. So popular people tend to connect with popular people, and less popular people have tendency to connect with less popular people. In the case of biological networks, nodes, for instance, if you look protein-protein interaction networks, nodes that are connected with large number of proteins, they have tendency to connect with the proteins that have relatively low number of connections. I don't know if I'm clear.
No, that was really clear.
Okay.
So also, sorry, I don't want to understand, but I just realized something. I just want to confirm. Would that mean in biological systems, there would be a lot of these clusters where all these nodes with a lot of connections to nodes with less connections,
Yes.
just cluster together?
This does not influence community structure. Actually, communities, or these, as we call them, clusters, so these are group of nodes that are more connected with each other than with the rest of the network. They come up, you can find them in biological and in social networks. So these two processes are not necessarily related to each other.
Okay, thank you so much.
Okay, thanks. Okay, so what I wanted to show you now is actually how you can use NetworkKit to really analyze one social network. And I will show you how you can find communities, because community structure algorithms, there's like tons of them, okay? There are really large number of them. Some of them are implemented in NetworkKit. Some of them are also implemented the same in NetworkKit. And the more complicated the search for these communities are, they're slower. And the beauty of NetworkKit is actually that they parallelize some of these algorithms, and you can actually find communities in a quite fast way. So what I used is a LiveJournal social network. This is a social network that has ground truth communities. I shared these ground truth communities with you too, but I'm not going to use them in this hands-on, because it takes a little bit of more time to relabel them and actually use these data to compare with real networks. But I will anyway show you how you can actually compare community structures that you found using yet one algorithm and using the other algorithm, and how you can actually see whether your analysis is actually bringing something interesting. So we usually, what we do is we read the data set. Usually the data come in as a kind of edge list. This means that you have a source node, a target node, and if the network is weighted, then usually you have a third column that gives you the weight of the link. But in this case, we are talking about social network that doesn't have weight. So it's a friendship network. So LiveJournal is a kind of blog post where people were writing different kind of posts, but they also were able to explicitly say whether another user on the LiveJournal media is their friend or not. So you actually get a friendship network from this. If you go to large Stanford data sets, you will find different kind of data sets there. You will find social networks that also have weighted links. You will find social networks that are signed. So basically, you have an information whether the relation is positive or negative. And take a look at this link, because it has very, very nice resources depending on what you need or what type of research you want to do, I really, really recommend it. So we are going to read our edge list. And as you can see, we have sources and targets. The size of our system is has 19 million links. We will also use live journal community information. What I usually do with my students is that I try to push them, because in this community list, you can actually have a missing information, or you can actually have a situation where you don't have all nodes that are present in the other data set. And I usually recommend them to go through first cleaning the data. And here you can see how we use this. We have 80,000 nodes here. We will drop certain nuns in these data sets. And we will also compare the data with already the data from the edge list. I'm not going to go through all of these steps because I already created a network that can be used for this. And I'm going to go right away. You have a code in your final, this EuroCC final Jupyter book. And I'm going to go through right away and actually load the network from this third file called LiveJournalNet that I already prepared using all of these steps before that. So we are going to load. Oh, sorry, something happened here. I apologize. Okay. Huh. Okay, I have a problem because my file was okay. This is bad. I apologize for this. So let's continue with, I don't know what happened with the data, to be honest, because it was deleted. I really apologize. So let's create again this graph, and then I can show you how to analyze it, and then let's see what is going on with this. Sorry. We will go with hyperbolic network. Okay. So, what we have here, we can actually look at the overview of this network. So what we see is that we have a network of 5 million nodes. It has quite high clustering coefficient, and this usually means that it will have also communities. Its degree associativity is relatively low. Basically, it's a kind of 0. And it has a minimum degree, which is kind of relatively high, so around 5,000 nodes, and it's 0, sorry, and a high degree, maximum degree, which is 4,943 nodes. And then we have very average degree, which is a kind of relatively low. What we want to do is we want to find the largest network or largest connected component. And we will use this largest connected component to analyze certain network properties after this. If we look at the overview of this largest connected component, we will see that it doesn't have isolated nodes, doesn't have self loops. It's actually, here we see that 30% of our network is actually part of largest connected component. And for these reasons, we will use this largest connected component to actually see our structure. What we can do here is that we can actually use largest connected component. We can also use our original network, and we can calculate the so-called degree centrality. So this is basically a function that calculates the degrees of this network. We can also calculate both on largest connected component and our degree on our large network. And we can actually compare these degree distributions by looking at the number of nodes that have a certain degree. As you can see, of course, as expected, the orange is the whole network. But what we see here is that actually the largest connected component also has a very similar behavior to our original network. And we can actually then use either one of them to calculate our other properties of our network. The next property is the one that I mentioned that shows us assortativity. Unfortunately, unlike network X that can calculate the average neighbor degree of a network for each node, network X doesn't have this solution. So I actually wrote a whole function that allows me to calculate for each degree the average nearest neighbor degree of that specific node. And if we run and define this function, we can actually calculate for our specific network, we can calculate the degree and average first neighbor degree. And, oh, sorry. No. I have a mistake here. Sorry. We have degrees actually of 0 size here. So we will use actually an largest connected component, because in this case, we are sure that we don't have nodes of 0 degree. And we will calculate for this largest connected component how our dependence of average nearest neighbor degree depends on this network. As you can see, unlike our social network, our network here is actually disassortative. This means that average neighbor degree actually decreases with the degree of the node. Actually, to be honest, our network is disassortative, but with very small coefficient in this sense. So we usually say that if we see this kind of behavior, that our network is not neither disassortative or assortative in this sense. Probably the biggest disassortativity comes from these very low connected nodes. What we can also look at, while we can use NetworkKit to calculate the average clustering coefficient, we want to use, we want to actually see how average clustering coefficient of nodes depends on their degree, because usually this tells us a lot about the system. And what we will do is, again, NetworkKit doesn't have this kind of function, but we can actually use it to calculate. We can define our own function. So what we are doing here is that we go through all nodes that have more than one neighbor. What does this mean? This means that we don't take into account nodes that have only one neighbor, because they cannot form triangles with them. And we actually calculate the number of existing links between nodes, neighbors of one node, and we calculate the number of these links, and we actually divide them with the number of all possible links between their neighbors.
Marija, I'm interrupting, but there are some questions in the
okay.
Can you see the questions? Because
okay.
File names on web page or something.
It was saving completed upload. Wait. Yeah. Maybe I made a mistake. No. Maybe it will work now. Yeah, let's see. Thanks. Okay. Sorry, guys. I didn't. Okay, probably the file was corrupted before this, but I can show you actually how social networks now look like. We can just run the thing. Thank you very much. We can just run the thing now in again. In this case, the largest connected component is actually almost 99.7%. So basically, you will see that we can actually use both of these networks, or either largest connected component or the component, just to look at. So again, we have a degree distribution that is quite broad. So we will also look at average degree, or how average first neighbor degree behaves. And as you saw in our case, it was for this hyperbolic network, it drops down, but for this, it kind of grows up, okay? And that's why we have this assortative coefficient here. Here, degree assortativity is 0.14. And as expected, it actually grows, the average nearest neighbor degree in this case grows as it is expected in social networks with the degree. Also, our network has high clustering coefficient, and we can see how this clustering coefficient is behaving I'm going to change here because we're already using for LCC. We will see how it behaves with degree of the node. So this is how we calculate the clustering of one node, okay? But we also want to calculate the average clustering of all nodes of specific degree. And this we will do using this function. So I already wrote it. Basically, what we will use is we will calculate the clustering of each node. We know the degree of that node, and then we will use all nodes that have a certain degree, calculate their average clustering coefficient, and then plot this on a graph. We will do it here. Oh, sorry. We'll go a little bit LCC. So we don't. I left some rudimenters in the function. Sorry for that. And we will plot. What we see here is that our clustering, average clustering coefficient kind of decreases with degree, but not as fast as one would expect. Actually, in many social networks, the clustering coefficient decreases as a power of degree in the network. And here, I wouldn't say that this happens. So our network is kind of has a high clustering. It's 0.24. But for instance, if you look at the Facebook data on their social network, the clustering coefficient is even higher. Officially, the clustering coefficient can go from 0 to 1. But to be honest, 1 is a very rare situation. This means that all nodes in the network form triangles as much as possible. But in this case, we have a quite kind of high clustering. We can use network X, but I wanted to show you, because this network is quite high, and we can use network X, but network X is a relatively slow tool, okay? But you can use network X, that's not an issue, okay? You will be just slower. And now the interesting thing is community detection algorithms. As I said, you have nodes in the network that form kind of groups of nodes that are more connected with each other than with the rest of the network. And there are many algorithms that you can use. Louvain is the most popular one, and usually the one that is used the most. There is a function called modularity function, and Louvain actually optimizes and finds the optimal maximum of this function. Usually the problem with complex networks and complex systems is that they have large number of local maximas or local minimas. And due to this, you really need to find the best algorithm to optimize your function and find really the global maximum of that function. There are many algorithms that try to do this, and actually officially maximizing modularity on networks is NP-complete problem, but there are heuristic algorithms that enables their calculations. And there is a lot of talk about whether maximizing modularity is actually the best way of finding communities in the networks. There are other algorithms to find the communities. One of them is propagation label algorithm. Both of them have parallelized version in NetworkKit, and they're quite fast. So what we are going to do is I'm going to run first PLM, that's parallelized Louvain algorithm for finding communities in a graph. We can run it on our largest connected component. We can run it on our network or the whole network. Here you can use different kind of parameters that will allow you to use the most optimal approach for this. And gamma 1 is actually a resolution, how different your communities should be. Here, gamma is 0.1. That's a relatively low resolution for this, but it takes a little bit of time for this algorithm to actually calculate the community structure. So I'm going to, okay. So I'm going to use the most simple one so we can get the results as fast as possible, but you can play with this at home. Also, the number of iteration is currently set to 32. So this is how many times it iterates until it finds this a maximum, but you can also use other approaches, or you can play with this to get a better results. So one way is to actually call the function or define it, then run it, and then you will get the partition. So what does this partition means? So this is actually the information to which community each of your nodes belong to. NetworkKit has its own structure written for this. So it's a type of network structure partitions. I can show you, it's also shown downstairs, but just to actually show you how you can actually extract information from this. So our first 10 nodes are actually in the community that was labeled 0. And you can also look at the number of subsets. So this means the number of communities your algorithm found in the specific moment. Just to show you, if you run the algorithm again, remember here we found 1,183 communities. If we run our algorithm once more, we will get different number of communities. Why is this the case? Well, actually, Louvain and also this label propagation algorithm, both of them are heuristic algorithms and they're stochastic. So they always start from different initial conditions, and as a consequence of this, you get different results or different number of communities. How we solve this with these kind of algorithms? We usually calculate the ensemble. So we calculate, for instance, up to 10 or 15 different 10, 100 or 200 different community structures of a specific network, and then we look at in how many of these sets 2 nodes are in the same community, and based on this we can actually find the more stable community structure of these networks. Just to show you propagation label algorithm, you can call the community structure algorithm in this way, but you can also call the community structure algorithm in a more faster, so to say, way. So by detect communities, you will set your network, you will define the algorithms that you would like to run. Here we will use label propagation algorithm for community structure, and we will run it. We will run it on our data. As you can see, the propagation label algorithm for community structure found almost double number of communities. This is also one thing that is kind of problem with community structure, and that's that each algorithm has its own definition of communities. Propagation label algorithm has very different definition of communities than Louvain method, and due to this you will find different communities, and you will find different number of these communities. Just to show you that actually the propagation label algorithm also has is also stochastic. So we will also run one more, and we will keep this information because we are going to compare in the end. I show you how you can actually see how many. So this one, the second run had a little bit less communities, so 2,407 communities. And NetworkKit has its own measure how to compare 2 communities, or how to compare 2 partitions of a network. And it's called dissimilarity measure. And you can actually use this measure to actually compare two partitions of your network. So here I'm comparing two communities partitions found by the same algorithm. So this propagation label algorithm. And as you can see, they're quite similar, or their dissimilarity is quite low. On the other hand, if you compare two partitions found by propagation label algorithm and the other one found with Louvain, you will get, that they're not that dissimilar as one would, so to say, expect. And using these kind of approaches, you can actually look at communities that you find with your algorithm, and then you can also compare them with true community structure. What I can tell you right away, while we use these ground truth communities as an information to test our algorithms and how good they are, ground truth communities don't have to be anyhow related to community structure of the network, because the community structure of the network is something that we get as a consequence of dynamics in that network. This means how people interact with each other or how they develop friendships with each other, while these ground truth communities usually are a consequence of their explicit saying that they are interested in certain topics and this kind of stuff. So they don't have to be necessarily the same thing, okay? And just to say a few more things, we can also look at how the ranking of these communities based on their sizes look like. And here we see this is comparison between two types of communities obtained from the same algorithm, and we can also do the same thing for our communities found with different algorithms. This is a ranking. This means that the rank is downstairs, or is on x-axis, the size of communities. So we have few communities that are of the size of tens of thousands nodes, and then we see this very fast drop, and then we have communities that only contain one or two nodes, so only few of them. I also put mutual information. This is a measure that we typically use. So NetworkKit doesn't have this. This specific measure in it, but it's very useful. It's very often used to compare the partition of two whether it's the same algorithm, just two different partitions, or to compare the partitions obtained by two different algorithms. I really recommend you use this function because it's quite interesting. Here, I also, because we cannot use the specific partition structure that is made, so I also kind of made a function that allows you to translate the output that you get from NetworkKit partition to the one that you can use for mutual information. And when we translate this kind of information, we will see that, for instance, if we compare the nodes of the same, from same algorithms, but just different runs, they have very high mutual information, it's 0.94. And if we compare the partitions found with Louvain method, then we will get something that is slightly less, but believe me, this is still very high mutual information. What I want to just push you a little bit to look at, I will answer in a minute, is that look at link prediction. NetworkKit has very nice algorithms for link prediction. This link prediction is usually done based on certain indexes in the network. I really recommend you to play a little bit with this because it can help you to, for instance, find whether certain two nodes can be connected or not. Yes. Someone raised the hand.
I think I couldn't see raise hands right now. No.
Someone raised the hand. Sorry.
Yeah, but I think maybe.
Okay. So that's more or less it. I really, NetworkKit is very new, relatively new, but I think it provides very interesting tools to actually use GPUs in analysis of large scale networks. Of course, we need additional development, but I think it will go to this direction. That's it. Oh. There is a question?
No.
You're welcome.
So thank you for delivering such an informative talk and also a hands-on session. It's, I think, very helpful and insightful for all participants. Right now, I couldn't see any questions, I think. No, there is no question. Thank you again for the contribution.
Thank you.
Okay, now I think we can have 15 minutes coffee break now. Then we will continue with the next presentation. Thank you.
Thank you very much. Thanks. Bye-bye.